Hello and welcome. Today we're taking on a massive, complex, and honestly deeply fascinating subject. We are going to look at an incredible scientific data set that tracks global temperatures over the last 2 millennia. Now, when you first look at raw data spanning 2,000 years, it can look like a total chaotic jumble of intersecting lines. It's like a giant puzzle. But today, we're going to break down this dense data set step by step, tracking the data year by year. Okay, let's dive into this. I want you to just think about this question for a second. How do we actually visualize 2,000 years of history? It's a huge challenge. We're talking about condensing millennia of natural planetary shifts, seasonal variations, and centuries of changing climates into a single readable format that we can easily comprehend. To do this, scientists don't just plot raw thermometer readings. I mean, obviously, nobody was sticking a digital thermometer out the window during the Roman Empire, right? So instead, they use a very specific metric to track the changes over time. To really understand our master graph today, you absolutely need to grasp this core concept, the temperature anomaly. See, when we look at our data, the vertical axis isn't going to show you an absolute temperature, like, 15 degrees Celsius. Instead, it measures a departure from a reference baseline. Think of the zero line on the graph as the long-term historical norm. Any data point above the zero line just means it was warmer than the baseline, and any point below the zero line, well, that means it was cooler. This lets scientists clearly see the shifts and swings across vast stretches of time without getting bogged down by localized absolute temperatures. So here is our roadmap for today. We're physically walking through this timeline starting at the dawn of the first millennium at 0 AD, moving to 1000 AD, hitting the dramatic shifts around 1600 AD, and finally arriving at the modern era in 2000 AD. All right, here is our master data set, the temperature reconstructions and instrumental temperature records. Let's get oriented before we trace it out. Look directly at the left side, the y-axis. There is our temperature anomaly, measured in degrees Celsius. Notice the scale here. The baseline 0 is right in the middle, and the scale stretches down to a negative 1.2 degrees and up to a positive 0.8 degrees. Now, let your eyes scan across the bottom, the x-axis. That's our timeline. We're going to watch this data unfold year by year, starting all the way back at 0 on the far left and running right up to the year 2000 on the far right. Section 1, the early centuries, covering 0 to 800 AD. As we start to track this year by year from 0 AD up to roughly 800 AD, look over at the far left and notice how the lines behave. They're jagged, they're intersecting, and they're constantly fluctuating. They generally hover below our 0 baseline, mostly bouncing around between negative 0.2 and negative 0.6 degrees Celsius. This beautifully visualizes a period of natural chaotic variance. You see those sharp little spikes up and down, like that black line plunging steeply just past 800 AD or spiking up around 200 AD? It's definitely not a smooth, straight path. It is the natural ebb and flow of the Earth's historical climate data playing out year after year. Now, you might be wondering why there are so many different colored spaghetti lines charting all over the place. Well, the crucial point here is that these are not just random scribbles. They are distinct scientific models. Because again, we didn't have thermometers in the year 400 AD. Scientists have to rely on complex proxy data to reconstruct the past. Look at the legend for a second. The black line, for instance, is from the University of East Anglia. The dark blue and pink lines, those are from the Hadley Center. The orange line represents research by Moberg and colleagues from 2005, and the light blue line is from Esper and colleagues from 2002. So what we have are independent teams using completely different methods, creating these overlapping models. They don't agree perfectly on every single zig and zag, which is exactly why the lines diverge, but they all capture the exact same overarching trends. Section 2, the medieval warm period, 800 to 1200 AD. Notice what happens as we track the data year by year past 800 AD and look toward the year 1200, right up in the upper middle of the chart where scientists have literally placed the label medieval warm period. Now, what's really interesting about this slide is how several of our colored reconstruction lines, particularly the pink, dark blue, and orange lines, start to peak. They climb right up out of that lower negative territory and hover much closer to the 0 anomaly line. Actually, a few of the lines even briefly kiss or cross the 0 line right around the year 1000. It's a very distinct, visible upward trend recognized across multiple independent models. Section 3, the Little Ice Age, 1400 to 1800 AD. Guide your eyes downward now. As we cross the year 1400 and stretch all the way over to 1800 AD, the graph creates this massive, deep visual valley. Almost all of our reconstruction lines, the Hadley Center data, the Moberg data, the Esper data, They all plunge well below the baseline. We literally see these lines dropping down to -0.6, -0.8, and dipping heavily in unison. This broad, multi-century trough is plainly labeled here as the Little Ice Age. It's a stark contrast to the period that came just before it, showing a really significant extended cooling anomaly across the northern hemisphere. Okay, before we hit the climax of our timeline at the far right of the graph, we need some absolutely crucial context about how the data itself is being recorded. Up until now, everything we've looked at, the early centuries, the medieval warm period, the Little Ice Age, it's all been represented by solid lines. As we established, those solid lines are temperature reconstructions. But as we enter the modern era, the nature of the data fundamentally changes. Notice how we start to see dotted lines appear? These dotted lines represent the instrumental record. This means we are no longer looking just at historical reconstructions from proxy data. We are now looking at direct, real-world recorded measurements from actual instruments deployed by places like the University of East Anglia and the Hadley Center. Section 4. The Modern Instrumental Spike. I want you to keep this specific year in mind as we trace our timeline forward. 1850. Look toward the far right side of the x-axis. Right between 1800 and 2000, we hit this absolutely crucial inflection point. This is the exact moment in history where the solid lines begin to transition heavily into the dotted instrumental records. And visually, this is where the behavior of the data completely, and I mean completely, breaks away from the patterns established over the previous 1800 years. Look at the extreme top right corner of the chart. And this brilliantly illustrates the unprecedented spike of the dotted red line from the University of East Anglia and the dotted green-yellow line from the Hadley Center. It's a violent upward trajectory. For 1800 years, we just watched the lines essentially dance between -0.2 and -0.8. But starting around 1850, the instrumental record shoots straight up. It crosses the zero baseline entirely and rockets toward positive 0.8 degrees Celsius by the year 2000. It is literally a nearly vertical wall of data that completely overshadows the medieval warm period and breaks the scale of everything we just walked through. We've taken an incredible journey today, year by year, from the chaotic variants of the year zero up through the medieval warm period, down into the depths of the Little Ice Age, and finally, straight up the sheer cliff face of the modern instrumental record. The visual contrast between those first 1800 years of natural variance and this sudden, extreme modern spike is profound. Which leaves us with a really critical thought as we wrap up this explainer. Looking at that massive, nearly vertical trajectory right at the very edge of the year 2000, where do the dotted lines go from here? Thank you so much for joining me to decode this incredible data set. Keep seeking out the structure in the data, and I'll see you in the next explainer.